Hello everyone, my name is Panos Charalampopoulos. I'm a final year PhD student at DTU Space, working with Yorgos Lelloudas. And I'm going to be moving to Turku from October, so I'm going to remain part of the NOT family. My research field is transients, and specifically tidal disruption events. And I'm going to talk to you about faint and fast TDE called AT2020wey. Cool. So Tom gave already a nice introduction, so I can skip the basic stuff, but you got the idea. A star is getting disrupted by the immense gravitational force of a supermassive black hole in the nucleus of a galaxy. So the debris that remains bound falls back as a stream, which self-intersects, soaks, and gets accreted by the supermassive black hole. So it's speculated that both stream collisions and accretion produce electromagnetic radiation, and there is a transient flare in the center, in the nucleus of the host galaxy. So typically these events happen in supermassive black holes of this mass range, although there have been exceptions in both ends. Charlotte talked the other day about an intermediate mass black hole TDE, and my supervisor, Yorgos Lelloudas, have published a paper many years ago about a TDE happening in a more massive supermassive black hole, SASI 15L8. But these are the typical mass ranges. And TDEs are multi-wavelength. As Tom spoke about, they're bright. Some of them are bright in the infrared, others are bright in the radio, many are bright in the X-rays, but here I'm going to focus on the optical and UV regime. Okay, so as we started observing them in the optical UV around 2012, and as more and more events started being observed and studied properly, now the community knows that in general they are characterized by a blue continuum, and this continuum is dominated by broad emission lines of the order of 10,000 kilometers per second, emission lines of hydrogen and or helium and or those high ionization nitrogen and oxygen lines attributed to a mechanism called Bowen fluorescence. So after fitting individual event spectral energy distributions, we know that they have blackbody radii from 10 in the 14 to 10 in the 15 centimeters with receding optical photospheres, temperatures of 10,000 to 50,000 Kelvin, and peak bolometric luminosities in the range of 10 in the 14 to 5 times 10 in the 44 ergs per second. So if we take a better look at these events, they are well-studied events up until 2020. This is a graph of Matt Nicol from a paper of our collaboration, IPESTO. There are two events that seem to stand out as being fainter and faster than the rest. So these events are IPTF16FNL and AT2019QIZ, which are two events very well studied. They have several individual papers each other, and plus recently appeared on arXiv this event from Hinkle et al. With a peak bolometric luminosity of around 10 in the 43.5. So in this Matt Nicol paper about QIZ, we set kind of an arbitrary cut of what means faint, which is like this value, events less than, with peak bolometric luminosity of less than 10 in the 43.5. So it has been something that the community wants to know is what causes these faint and fast events. And one speculation was that there is a correlation between the black hole mass and these events, because this IPTF16FNL thing, it was measured to have black hole masses lower than the typical range I talked about before, masses 10 to the 5, and QIZ was in the lower end with 10 in the 6 solar masses. So these estimates have been done with different methods, but the more trustworthy one remains the M-sigma relation, which needs high-resolution spectroscopy in order to resolve the galactic absorption lines, measure their widths, and determine the black hole mass in the center. So another paper recently appeared in arXiv, this one of Hammerstein et al., which is a photometric population study of 30 TDEs discovered by ZTF up until 2020. So if we try and find which one of these events is the faintest, Probably you have already guessed that the answer is AT2020wey, an event discovered in the fall of 2020 by ZTF in a passive post-starburst galaxy in a redshift of 0.027. So I have been the PI of this event, and we followed it up photometrically and spectroscopically in collaboration with Yair Arkavi, and followed up with LCO. There are the public ZTF data and Swift as well. And you can see that it is a very faint event, for TDEs at least, with very faint peak, absolute peak magnitudes. And it reached host levels in the optical at least very quickly after 20 days post-peak. I don't know if this data are very trustworthy. So, faint and fast event. And after fitting its spectral energy distribution, we see that it has a bolometric peak magnitude of 10 in the luminosity of 10 in the 43 ergs per second, a bit less than that actually, and small photospheric radii. So to see how these numbers compare with the rest of the sample, this one in the red is AT2020wey. I don't know if you can see the colors properly, but I want you to focus on how identical it looks underneath its IPTF16FNL that I talked about. So it looks kind of, its clone in bolometric luminosity, evolve kind of in the same way. And it clearly is the two faintest TDEs up to now. So one thing we wanted to do is to measure the black hole mass in order to check if there is a correlation that I talked about before. And we did that with MOSFET, the modular open source fitter for transients, and which gives a model-dependent estimation of the black hole mass. And this is what we find, 2.16 which is in the lower end of typical black hole masses, but not that low in order to support an argument that this black hole mass can give the faint TDEs. And here's where I wanted to talk about NTE, which have been crucial in such type of studies, because up to now X-Shooter is the instrument that is used in order to get high resolution spectra and measure the black hole mass. So if we had NTE, we could use it for this northern target and try to more properly constrain the black hole mass and see this scenario. But yes, with this black hole mass, we cannot really say that this is the reason for the faintness of the event. Okay, now to the spectroscopy. We followed it up with Floyd's on LCO and with my program in the NOT with ALPHOSC. And this is the spectral sequence. In the left is the host subtracted spectra. In the right is the host and continuum subtracted. Same spectra in both ends. And we can identify broad H alpha emission. And we can also identify H beta and helium-2 lines. But this wouldn't have been possible if we relied to the LCO spectra. And I want to show how crucial it was to get this spectrum with a NOT, with my program at 9 days post-peak. And so with this spectrum, we could robustly spectroscopically classify this event as a hydrogen plus helium event, because we could resolve that there is this typical helium-24686 line in the spectrum. And apart from that, we were able to properly compare it with the spectra of the other two faint and fast TDEs that I talked about, and see that this one does not show this highly ionized Bowen nitrogen-3 lines that the other two show here. So this NOT spectrum was very crucial in order to, first of all, rule out any correlation between the emergence of the Bowen lines and fast and faint TDEs, because the previous two had these Bowen lines, while 20wey clearly doesn't have, and also to properly compare it with the other spectra and see that, especially with 16FNL, they look very similar spectroscopically in everything apart from the emergence of the Bowen line. So this is something interesting that we're trying to figure out. And to return to the Hammerstein paper that appeared on arXiv, we were wondering if events like this one, faint events, would be gone unnoticed in searches for bright nuclear flares of the order of -20 to -19 absolute peak magnitudes. You can see here are clearly very populated. And if there is if they are underrepresented in classifications and in sample studies. Also, we wanted to check if there is a missed population of such faint TDEs that could help in relieving the so-called TDEs rates tension that Tom quickly brought up, that theoretical studies were predicting an order of magnitude higher rates than what we observe. And only recently we have managed to reach the lower theoretical limit. So what we did is that we took the public CTF data of these same 30 TDEs and we created these histograms. On the left is the G band, on the right is the R band. And but in order to, and we color code for those events, this is an arbitrary cut, but we color code for those events that are fainter or equally faint for from AT2019QIZ. And so in this sample, there are 3 events that are fainter, including QIZ. But when we do such histograms, we need to consider observational biases. And there could be that, there are faint TDEs that happen in larger distances, and they are faint enough for us not being able to observe them, what is called the Malmquist bias. So in order to consider this, we have to normalize the numbers to the same co-moving volume. So we performed a volumetric correction, which is for each TDE, which is the ratio of the volume probed by the intrinsically brighter TDE in the sample to the volume probed by each individual TDE given the limiting magnitude of the survey, which means the luminosity distance that we would observe each TDE in this limiting magnitude. So, okay, so I have to state that these are really just out of the oven results. They're very preliminary, but they can give us an idea of what's happening. So on top you see the actual sample, and on the bottom is the corrected, the volumetric corrected results. And so we can clearly see that the faint events are underrepresented, and that their numbers must be much higher than what we consider normal at peak, at least. So here, I don't know if you all can see the numbers, but I have the mean absolute peak magnitudes before and after the correction, and they drop almost, they're smaller by 1.5 magnitudes, where the mean peak shifts. And in the initial sample, we have 3 out of 30 TDEs being faint, while after the correction, we go up to 56%. And yeah, of course, there are caveats here. These are low number statistics, and we haven't had the time to correct for K correction, but these are things that we are properly gonna take care in the presentation, which is in the publication, which is in process. And one more thing we want to do is, based on these results, we want to try, give it a go, and make an estimation of the rates that we could observe these things. So this is it from me. Thank you very much. And if you have any questions.